Our next speaker is Dr. Steve Benner. Dr. Benner is an internationally renowned expert in both astrobiology and synthetic biology. He has had a long, diverse career in both academia and industry, including founding a number of very successful biotechnology companies. And Dr. Benner is going to speak with us this morning or evening, wherever you might be, about the very early days of the Earth and the chemistry that we may have found or not found there. Thank you, Steve.
Okay, so all right, excellent. Well, let me just talk about, right, obviously we're worried today and tomorrow and Wednesday about this thing called life. And for sure, life has something to do with information. It has something to do with evolution. It has something to do with chemistry. There you go. So, but the necessary problem is we can't just talk about them. To develop these generalities, we need some surprise inputs from experiments and unguided observations. And this is these wonderful two books, very influential books by Roger Ock, who talks about experimental and unplanned observation as providing you a kick in the seat of the pants or a whack on the side of the head. It's important to understand these two things, like information and evolution, both have problems when it's associated with trying to get experimental input. So I actually put one of these this is from a quote from Sarah Walker and Paul Davies about information, who notes that although it has been notoriously difficult to pin down what makes life so distinctive, its informational aspect is the key property. Here, they propose that the origin of life may correspond to a physical transition associated with a shift in causal structure where information gains direct and context-dependent causal efficacy over matter it is instantiated in. And then there's a bunch of equations. And so a good chemist like me, we are sort of knuckle-dragging people, look at these equations and say to ourselves that such physics-friendly formalisms suggest actually very few experiments. Evolution has a different problem. Remember, a lot of evolution is sort of just those stories about the historical past, where the historical past is contingent. Since time travel is not accessible to us, except into the future, many of the experimental scientists, especially from my neck of the woods, find these are not wholly what we'll call scientific. Now, I realize there's some evolutionary biologists who are listening in are going to give me a lot of trouble on this, but that's sort of the idea. So what we did about 10 years ago is wrote a non-impactful group book. That's this book, Life, the Universe, and the Scientific Method, to address such problems. And I'd like to talk to you about 3 or 4 ways in which the book suggests that we might resolve this problem to understand this stuff called life in the center of this. Of course, one is that the bottom wedge is to look at the life that we have on Earth and to understand its evolution in part by working backwards in time to a minimal life form. And as I have shown in magenta here, that life form is likely an RNA world. That's a form that RNA was used for both genetics and for metabolism, catalysis for metabolism. Of course, we can do the opposite. We can work forward in time in the origins of life. That's the top wedge, where we try to get basic small molecules, some of which Lisa mentioned a moment ago, to self-assemble them to give RNA. Or in the right wedge, we can try to go back and create our own Darwinian systems, sort of an artificial alien life, hoping to learn what universal features, structural features, biosignatures might be present in informational molecules that are supporting life, no matter what its origin is. And of course, the left-hand wedge is sort of what we're all interested in doing, and that is seeking second examples of life by exploration, using the biosignatures that we've come to understand by looking at modern life on Earth, its origins, and synthetic life forms. And the end point of this talk, which I'll just mention briefly, is that we've gotten a good idea about going backwards in time to come up with this model of an early episode of life on Earth where RNA was very important. We actually have reasonably good models now that say that about 4.36 plus or minus 0.05 billion years ago, RNA arose to support Darwinian evolution in a post-impact environment in the Hadean. We actually have, and for the right wedge, artificial systems that are capable of supporting Darwinian evolution, and we have learned universal biosignatures by asking what, if, or why not questions. One of those is polycharged backbones in their informational systems, and we'll talk about aperiodic crystal structures into which these fits as universal ways of looking for life, at least in water, at least where we can access the water directly. So let's dive into it. I want to mention a little bit about paleogenetics because it's actually how we bring experiments to history. And you got to keep in mind is that, if you look at these DNA sequences or protein sequences that are now available to us in abundance, they actually look informational. They look like letters written in a line. They look just like you would look at a binary code, except they have more symbols than binary codes. I've just thrown on the slide here parts of the informational molecules. These are actually sequences of amino acids where the one letters are representing one of the amino acids in the protein sequence. These are from the enzymes that you have in your body to metabolize alcohol when you drink wine or beer. And there's a human enzyme, a tarsier enzyme, there's a lemur enzyme, and there's a mouse enzyme. And we can manage this as if it were just information, right? We can manage it using Markov models where we have site-independent replacement of amino acids by other amino acids. And you can see in red in those sequences where those replacements have occurred since the common ancestor, which lived about 100 million years ago. We make the assumption, as a good Markov model does, that future replacements are independent of past replacements. And the replacement probability at a site is the replacement probability overall. And one can go back and do experimental analysis of existing sequences. This was actually started many, many years ago by Margaret Dayhoff, where we have, and we actually did this published in Science. Actually, people know about this work, so I won't talk about it because it's not published in a lesser journal, as we like to say. But this is a matrix which just has some statement about the probability of every one of those 20 amino acids being replaced by every one of the other 20 amino acids as a function of divergent evolution in proteins that are divergently evolving under functional constraints. Now, that's an empirical observation. We're looking at lots and lots of proteins, but what we can say is that we can get from these parameters that allow us to infer probabilistically the sequences of ancient proteins from extinct organisms. And then through the magic of recombinant DNA technology and DNA synthesis, we can resurrect those ancient proteins for lab study. And then we can use those ancient resurrected proteins as a sort of a Jurassic Park experiment to understand or study evolutionary hypotheses or models. So just going back to those four mammals, we know about when primates began to digest alcohol, ethanol, because we have actually resurrected the ancestral alcohol digesting enzymes. And going back to this tree, all the enzymes in blue do not oxidize alcohol very well, and the enzymes in magenta do. We know the mutations that occurred about the same time that humans started to walk upright in that bottom of the tree, where mutations were made that made the enzyme, instead of not taking ethanol, able to take ethanol. And so we roughly began to know when you started to drink alcohol. And that means we know something about your past history by actually resurrecting bits and pieces of the enzymes in your ancestors. Now, the conclusions of this are rather obvious, all right? I mean, evolution basically solved every problem that it was faced over the last billion years just by random changes, or at least non-prospective changes in the biomolecules. This is just an example of a tree that we worked with Eric Gaucher to put together. You're actually going back now billions and billions of years. You're looking at proteins, the elongation factors that worked with RNA, the ribosome, which is that molecule on the upper right-hand side of the screen, with the orange parts being RNA, the blue parts being protein. This is an RNA catalyst that makes proteins. And we can tell you by looking at the temperature optimum of the enzymes that we've resurrected, what temperature various events occurred at for example, what temperature the organism lived at when the mitochondria went into the cell, when the chloroplast went into the cell. And again, this is published in non-lesser journals, Science and Nature, so everybody knows about it, so I won't talk about it in great change. Now, there are surprises and there are puzzles. The RNA world has proven to be remarkably robust in these resurrections. The Markovian model is behavior, however, is easy to find, and when it's found, it provides signals for sequences that are not directly informational, like folding and function. The inferred ancestral enzymes are also often very stable. I'm referring to some work here by Danny Tofik. But there are some mysteries, but not many. They're puzzles more than mysteries, because once Darwinian evolution is in hand and life is challenged, as Jeff Goldblum in The Real Jurassic Park says, life finds a way. Everything is easy once you get Darwinian evolution is in hand. And that's likely also true for even things like origins of intelligence, or I'm listing here some of the classic milestones in vertebrate evolution. How fish got jaws, for example, or how eggs with membranes evolved membranes that breathe oxygen without losing water. And so that means that if life always finds a way, the mystery actually we have, if that's the power of Darwinian evolution, the mystery we actually have is in origins. That is, how do informational molecules that access Darwinism, like RNA, emerge on a Hadean rocky planet? And the mystery comes from two very well confirmed observations. The first one is that absent Darwinism, organic material degrades to tar. You see this yourself in your kitchen all the time when you try to cook breakfast and leave the heat on too long. But present Darwinism, the same organic materials can evolve to occupy all niches as long as they have some energy and some solvent. And so the paradox is, how the hell does RNA emerge with its Darwinian potential before its precursor organics do what they do in your kitchen when you put too much heat on the souffle, devolve to tar? And that's the big paradox, because in general, if you start getting organic molecules, you put energy into them, and you don't have access to Darwinism because it's pre-life, you don't get life, you get tar. So with the Hadean Earth, we have to ask what we have to work with to try to prevent the organics there from forming tar and trying to get them to actually give you Darwinism, or at least molecules, informational molecules that support Darwinian evolution. So this is known to most of you. Earth formed, the moon a little later, the iron core sank. That removes most of the reducing metal, iron 0. The iron 2 that remains, some of it disproportionates to iron 0, and that sinks further. And so by 4.36 billion years ago, the mantle is relatively oxidizing. So what the geologists speak of is what's called the phaolite magnetite. That is iron plus 2, and a little bit more. That means that phosphorus is not phosphide, it's phosphate, PO4. Borate is not a boride, it's borate, BO3. Silicate is silicon dioxide. And also that the atmosphere has carbon in the form of carbon dioxide, not so much CO, very little methane. Nitrogen was N2, not ammonia. Sulfur was SO2, not hydrogen sulfide. And hydrogen is water, not H2. And we know that because we actually have little pieces of the Hadean Earth from this antiquity in the form of zircons that survive. And Dustin Trail has measured the ratio of redox active elements like cerium and showed this statement. By the way, this has all been published, but it's been published in a lesser journal, as we like to say, so it's had relatively little impact. But if you want to know the details about how we can date these things, there's a nice review article that we put together with Dustin. Excellent. Now, that Hadean material governs what organics were available to initiate RNA synthesis and what minerals were available to prevent those organics from devolving to give you tar. And again, one of your problems with RNA is that R is ribose. Ribose is a carbohydrate, it's a sugar. You know from your work in the kitchen, and if you heat sugar, you get tar. There is, in fact, on the right-hand side, a picture of the caramel that you get, brown stuff. But in the presence of borate, and this is the structure center left on the slide, borate minerals bind to adjacent OH groups, which are in carbohydrates. When borate binds to the adjacent OH groups in ribose, it forms a very stable borate complex. So borate stabilizes ribose under the conditions where it is formed. And that's also been published and not in lesser journals. And so it's people widely know about it. People now have looked for borate on Mars, for example. Borate is actually found on Mars. And Benoit Prieur, who actually himself also had this idea independently of us, finds it a very important discovery in prebiotic chemistry. This is how you prevent a certain class of molecules from becoming tar in a Hadean environment as long as you have borate minerals, which we now know are there partly because of our exploration of Mars. So the hard problem is actually making and stabilizing oligomeric RNA. There is again that oligomeric RNA with the pretty colors. One of the things that Elisa Biondi found was that one way you could stabilize it is by using minerals where silicon now is in the oxidized form, SiO2. I've shown you a pretty example of gem opal, which is reprecipitated silicate. It's what you get in Australia, for example, but also in a Hadean Earth where you have a semi-arid region. And it turns out that RNA is absorbed onto this mineral and is stabilized. Again, it's published in the lesser journal, so not many people look at it. One of the morals of this talk is that you should forget our papers in Nature and Science. Our important stuff is in these lesser journals. But the point is that silicon is present as its oxide on the Hadean surface. Silicon dioxygen, not iron silicide or something like reduced form, and that's available to stabilize RNA. But of course, now that just raises the question, can RNA be made in the Hadean? And yes, the answer is clearly yes. By the way, this result has proven unpublishable because of the dreaded third referee. I'm sure you've all had this problem. I can't tell you as a result the specific Hadean environment where RNA forms because it hasn't been published yet. But I can tell you who got the results. That's Elisa Biondi here. So if you want to know how this works, ask her. But I can show you that this reaction below, that is, if you take our ribonucleoside triphosphates and you put them in the Hadean environment, you can actually get oligomeric RNA. And I can prove it to you. So if in case any of the third referees are listening, here are some data, some of the proofs. You're looking at a gel where you're looking at a time series. We're incubating for up to 144 hours these precursors in this Hadean environment, and we're making oligomeric RNA, which is at the top of that gel. The graph on the right shows the time course of that manufacture. We actually measure kinetics of RNA formation under Hadean Earth conditions from nucleoside triphosphate precursors, and mineral catalyzed processes are making, with measurable kinetics, make oligomeric RNA over days. In fact, it continues over months because remember, we know how to stabilize the RNA after it's formed. And that's again, Elisa Biondi's work. So we know this because, among other things, the RNA product is degraded by ribonuclease, which is an enzyme that degrades RNA. And now you're looking at just polymeric A, G, C, and U, and mixed NTPs being degraded by RNA. Again, Elisa is the person who did the work. These products are ribonucleoside 2' and 3' phosphates, by the way, for those of you who are chemists in the audience. And these can be made only if the triphosphates are converted to linear RNA with 2', 5', and 3' 5' internucleotide linkages. And for the chemists in the audience there, you're seeing the degraded products from RNA made from triphosphates under Hadean conditions where we recover the products in a degradation scheme. So that means that oligomeric RNA with Darwinian potential can emerge in the Hadean environments from nucleoside triphosphates and stabilized. There's Elisa again. But now, of course, the obvious question is, great, how do you get the nucleoside triphosphates? Well, the answer is that that's actually relatively straightforward. And you have to discuss what phosphorus is on the Hadean Earth. And we're going to have a discussion of this, I saw in the program a little bit later. But there's a great article, again, not published in it was published in a lesser journal, so you have to go dig for it, from Niels Holm in 2014, where they talk about volcanic glasses as sources of condensed phosphates. And what we have here on the right in magenta or purple is cyclic trimetaphosphate. That's a popular form of phosphorus in basalts that would have been present on the early Earth. And it turns out that if you take a nucleoside base on the left, coordinated with the green boron at the bottom for stabilization, and you put it in the presence of nickel and tricyclic trimetaphosphate, you make the triphosphates, and that's the precursor for the reaction that you're going to have to ask Elisa how it happened that makes RNA in the Hadean. And these are also not published, however, in very prominent journals, so you're going to have to dig it up to go see the data. Great. So you say triphosphates and RNA. But that's, of course, raises the question, if I can make triphosphates from nucleosides stabilized by borate, where do the nucleosides come from in the Hadean? And what's kind of interesting about that is it's actually very easy as well. And this is actually something that was published again in a lesser journal by Hyojun Kim and his son, actually, who was doing an internship with us, Justin Kim, where if you just take that cyclic ribocyclic phosphate on the left-hand side of the screen, and you treat it with the nucleobases that are shown in blue, cytosine, uracil, adenine, and guanine, you put the base on in the presence of calcium evaporation and urea. It's actually a very simple reaction. It works more or less in water. By the way, the reaction that takes the cyclic trimetaphosphate also works in urea and water in the presence of nickel to make the triphosphates. And that makes the RNA in the reaction that you're going to have to ask Elisa about. So that's kind of cool, but then that raises the question, how do ribose cyclic phosphates form in the Hadean? So here I am, you see what I'm doing here? I'm working backwards. We got RNA from triphosphates. We got triphosphates by cyclic trimetaphosphate reactions in the presence of nickel with the borate stabilized nucleosides. We got the nucleosides by reacting the bases with the cyclic phosphate. Well, how does ribose cyclic phosphate form? Well, the answer is that, again, is cyclic trimetaphosphate. This is actually old work. It goes back to the year 2000 from Ram Krishnamurthy. If you just take cyclic trimetaphosphate with a little ammonia and ribose, you make the cyclic phosphate of ribose, which then reacts with the bases to make the nucleosides stabilized by borate, which react with cyclic trimetaphosphate to form the triphosphates, which, and Elisa will tell you how you make RNA. So then the question is, how does ribose form in the Hadean? Well, that's, of course, the borate modified carbohydrate synthesis, which we spoke about. Now, I want you to notice recurring themes. I'm not doing a lot of different stuff here, right? Basically, I'm just talking about the same thing over and over again. This cyclic trimetaphosphate, the borate, urea, again and again. The only thing we need are oxidized minerals and organics in forms expected in basalts and gases, escaping from a phthalate, quartz magnetite environment. And the process moves from simple carbohydrates to RNA as an intrinsic outcome, what you naturally expect as a natural outcome of Hadean geology. And there's that whole process that I just described to you. But you got to be careful. I've actually pulled a fast one on you. We are using oxidized FQ mantle and its rocks, but we're paradoxically also using the reduced nitrogen compounds, that is the bases, and the reduced nitrogen compounds that are the precursors of the bases, the blue compounds in the upper right-hand side of the screen from the atmosphere. And this is a contradiction. We're using an oxidized mantle with oxidized gases and oxidized minerals on the surface, but we're requiring the atmosphere to deliver reduced compounds. And that is a serious paradox. In fact, it's a big paradox because these compounds have always been seen as easy by prebiotic chemists, as they are easily made from hydrogen cyanide. The bases are easily made from hydrogen cyanide, cyanoacetylene, these other compounds. And this is actually a very famous mechanism for the formation of adenine. It's from John Arrow. And so you have whole groups of people assuming that you can get these molecules, even though the atmosphere is above an oxidized phthalate magnetite mantle, have none of them in them. And so that's a paradox. But you got to keep in mind that this Earth is not sitting there unattacked. In fact, it's being bombarded by impactors, say the size of Ceres, say about 10 to the 24th grams, or say the size of Vesta, about 10 to the 23rd grams. They have their own iron core. And of course, when they hit the atmosphere, they shatter that fragmented core, and it puts a large amount of iron 0 into the atmosphere. And what that does is reduces the atmosphere above an oxidized surface, making large amounts of hydrogen cyanide, ammonia, carbodiamide, and cyanocetylene, and these RNA bases. This is actually a great thing that Dave Catling and Kevin Zonley did for us. You can actually see how this works. You're looking at a time after impact. This is a Pluto-sized impact. Between about 2 million years, right, you have hydrogen cyanide formed, and then it goes away. Hydrogen is formed, of course, that's the red line, and it eventually distills into space. But for 2 million years, you have the opportunity to make the reduced nitrogen compounds and the nucleotide bases above an oxidized planetary surface. And this is a great thing. And of course, we have outlined this, again, published in a lesser journal, but that's a reference if you want to see how this particular stuff works. So what that means, of course, is that this is determining the timing of a productive Hadean environment. I mentioned that this occurred at 4.36 plus or minus 0.05 billion years ago. And you might have thought I was joking, but actually I was not. We have a reasonable idea of the impact history of Earth. And so we know that much larger impacts, of course, are going to form magma oceans and going to cause redifferentiation of the core, like when the moon was formed. And of course, much smaller impactors later in history are going to not produce a very long time period of productive atmosphere. But what's going to happen is eventually the productive atmosphere will go away as hydrogen escapes to the cosmos. So this is how RNA can emerge in the Hadean. This is why we say when it's most likely to have emerged in the Hadean. And in this in this lesser journal here, you can look at you can actually go back and look at this article, which we have provocatively titled "Prebiotic Chemistry That Could Not Have Happened." This is stuff that absolutely certainly happened on the rocky planet. And it leads to a very brief period of time, 2 million to 5 million years, depending on the size of the impactor when life can emerge. So this is a model now for the autonomous formation of RNA as a natural outcome of post-impact Hadean platforms. And so the question is, you can ask, is this universal? Well, now we've invoked general principles for rocky planet formation in this model. That's core differentiation, the sinking of the iron is very rapid, its timing is universal, the rocks are therefore more or less universal. The impacts certainly occurred universally. This is, by the way, common for Earth, Mars, where, as I mentioned, we still see parts of this. We still see the borate. We still see on the surface of Mars some fragments of what we're modeling here because Mars has not had the plate tectonics to bury them. And of course, it also is true for early Venus. David Grinspoon will talk in a little bit about this, maybe tomorrow or the next day. So the experiments show RNA formation from CO2 it's ribose, by the way, not arabinose that is made, not glucose, not lixose, not any of a number of other carbohydrates that are possible. Now, we do see some diversity in bases for sure, but perhaps in expanded alphabets. But this is universal. By the way, it's not obviously universal for ocean worlds like Europa and Enceladus because they don't have dry subaerial land necessarily. In fact, we don't really know their early environments well. And so we have to define informational biomolecules. What will they look like in these other worlds, which still have water, but do not necessarily have the subaerial dry land that we have? Now, synthetic biology is how we turn to define what informational molecules might support Darwinism on Europa or Enceladus, where we do not know the origins. That's this right-hand side of the plot I put here, and it leads to what we call agnostics life detection. Now, I'm not going to talk about this because we don't have time. We have made many alternatives for DNA and RNA. Some store information, some evolve, others not. But by examining these synthetic systems, we can discern structural features that will be universal for all evolvable informational molecules working in water to support Darwinism, regardless of their origins, regardless if they had this phalite magnetite crust beneath a reduced atmosphere. So I'm not going to spend a lot of time on this. We have published this in very visible journals. Everybody knows that we have a 12-letter synthetic informational DNA molecule that supports Darwinian evolution. How do we know this? Well, we know that it supports Darwinian evolution because we have evolved it to bind and deliver, to bind to cancer cells and deliver drugs there. You could argue that this is an alien chemical system capable of Darwinian evolution. We've not found it in the cosmos. We have made it in the laboratory, but that's a much for argument. But what is important here is that we have also discovered what we cannot change. We can change the bases, we can change lots of features, but we cannot change two things. The first is that we cannot change the fact that all informational units must have the same size and shape in an evolving informational Darwinian polymer. And the second thing is that the backbone supporting these units must have a repeated charge because the interchanging the units must not change the overall molecular properties. Now, the first statement, you can take these, by the way, as experimentally validated statements because of the molecules that we have made. However, they also have strong theoretical support. Let me mention Irwin Schrodinger for this point, very famous guy for quantum mechanics. By 1943, he was slumming, doing molecular biology. He actually knew nothing about the structure of DNA, but he also knew that simple binding cannot guarantee faithful information transfer, at least not the amount of information that is needed for life. So for that, Schrodinger realized that he needed the physics of phase transitions, which for those of you who do physics of phase transitions, you know they are marvelous, marvelous things. And for that, Schrodinger recognized that the exchangeable informational building blocks must all have the same size and shape because they must all fit into the same aperiodic crystal structure. So that means that Martian DNA may have 4 units or 6 units or 8 units, but to support evolution, they must all have the same size and shape. And that's one way you know that you have a biopolymer. But there's another thing we can't change. We cannot change the overall molecular properties of this. And for this, you have to go back to my non-impactful book, Life, the Universe, and the Scientific Method, to go back and understand why those polymers are rare. But one feature that allows biopolymers to be informational and Darwinian, to allow you to replace building blocks and therefore change the information without having the things precipitate, is to have the backbone have a repeating charge, a repeating positive charge, or a repeating negative charge. It must be a polyelectrolyte, as we like to say. So all life has informational polymers. That's why information is important. But these are not just any polymers. They must have size, interchangeable building blocks, and they must have in water a repeating backbone charge. And we know this because of theory and synthetic biology. And of course, is confirmed in Terran life, although that is hardly necessary. Now, so here's a quiz for you folks. If I were not virtual, I would look around the audience and see who is still awake. If you want to find life on Mars, Europa, Enceladus, what must you look for? And the answer is a polymer with repeating backbone charges assembled from size, interchangeable building blocks. And by the way, you'll find this in Martian water permafrost. And in fact, this forms the basis of an agnostic life detection, which has the useful acronym ALF. And the repeating charge is very, very useful because ALF can exploit the repeating charge feature of universal DNA or RNA to remove any alien DNA from a continuous flow of water. We've actually put this up in Primordial Scoop. It's about to be published in a lesser journal, so you can go look at it there. Fundamentally, what you're going to do is flow water in the top, and then you're going to move the negatively charged polyelectrolytes to the left, if Martian life has DNA or RNA, or if our Martian life has chosen a different charge in the backbone, it's going to move the charged species to the right. And you'll be able to recover them. And then, of course, you'll be able to examine them to see whether their building blocks are built from size, regular building units that fit Schrodinger's aperiodic crystal structure. So this is how we can look for alien life on Mars. This synthetic biology defines what alien life DNA looks like by making alternative forms of life. Alien DNA must have a repeating backbone charge. The highly charged molecules are easy to isolate from water. The agnostic life exploits these facts, but, and this is the phrase that's going to get me into a lot of political trouble, NASA will, in my lifetime, I'm convinced of it now, will never likely ever build an ALF. I mean, for 45 years, NASA, as you know, has declined to look for alien life on the place most likely to have it, using tools able to unambiguously detect it. We're instead flying toy drones, we're flying missions to Europa without adequate life detection concepts. Sorry, Lisa, we're seeking extrasolar planets where every information you get, you're never going to get a definitive answer. But in fact, if you go to Mars, you're going to be able to find life on Mars. And by the way, SpaceX might find it. And we're actually looking, the introduction mentioned collaborations. Anybody who wants to collaborate, we're ready to collaborate. And you can see more about this on our web blog, primordialscoop.org. It turns out that SpaceX, maybe even NASA or the ESA, or maybe the Chinese Space Agency, will want to send people to Mars. And they will, actually, it turns out that they will want to bring them back. And so to bring them back, they need to generate fuel in situ. Methane, oxygen fuel is what the SpaceX program is presently designed for. They make methane oxygen fuel by taking carbon dioxide from the atmosphere, reducing with hydrogen that's generated by electrolysis of large amounts of mined water. And so this is exactly what ALF needs. We need to have a large amount of water to look at, because the more water we look at, the more our chances of finding Martian biology. Mars has lots of water, okay? There's a subsurface permafrost. On Earth, this permafrost would hold ALF-detectable life. SpaceX must mine lots of water to make fuel in what's called the Sabatier process, which I just described, to make methane from carbon dioxide. This mining must be running before the first humans arrive. And that means putting ALF between the water mine and the downstream process is a way of getting life detection to occur before we contaminate Martian biosphere by human visitation. So that's all I have to say. That's what I have been doing for the last 30 years of my life. What have you seen? Well, life does have something to do with information and evolution. And when the details of evolution of bioinformations on Earth are finally worked out over the next century, we will undoubtedly find that they were created by natural selection working on biomolecules encoded directly or indirectly by informational molecules suffering non-prospective changes. That's Darwinian evolution. Of course, we're now doing Lamarckian evolution in human evolution, but never mind. The Jurassic Park paleogenetics resurrections will help providing experimental surprises here. But life finds a way. And so there's going to be a lot of puzzles, some of them very interesting, some of them very difficult. But I don't think there's going to be any paradoxes. Where the paradox lies is in origins. How do you prevent material from turning into tar in your kitchen before it gains access to Darwinism? But a coherent model exists for how RNA is made as a natural, possibly unique outcome of post-impact, very important post-impact chemistry of rocky worlds like Earth, Mars, and early Venus. Whether life persists depends on whether it finds a way. So synthetic biology now lets us talk about universal biosignatures independent of origins. That is, we've got to be looking for things that have repeating backbone charges and regularly sized Schrodinger building blocks. And life on Mars could likely be found today if only someone would look for it. With that stop, and a lot of this is also in our primordial scoop, which is not refereed, not even in a lesser journal, but let me stop there. Thank you for your attention and be happy to answer any questions you might have. And let me stop.
Thank you very much, Steve, for a wonderful talk. As someone that doesn't work directly in this field myself, it's always remarkable to see how much progress is being made on a problem that, from my perspective, seems almost intractable. But amazing stuff. And I also personally appreciate the provocation there at the end. That was also very welcome. So we have a question from Jill Tarter. Maybe we'll start with this. Has synthetic biology answered the question about what is necessary versus what is contingent in life as we know it?
Well, in genetic biopolymers, I mean, you're talking to a guy who thinks he has found the answer, and that's always dangerous, right? Because I'm going to say things from my own research, which are probably not the things that should be, they should be questioned. But yes, I mean, certainly I think from the point of view of what's universal in genetic biopolymers, the concept of a repeating charge in the backbone, the concept of a Schrodinger uniform building blocks, I think that's a universal. By the way, synthetic biology otherwise has found extreme diversity. So at least it talks about the diversity of life, but of course at the molecular level, Terran life is not diverse at all, but we can find many different amino acids, many different lipid structures, many different membrane structures, many different nucleobases. I showed you a 12-letter genetic alphabet. And so at the details of Darwinian bioinformational biopolymers, there are really only two things that are universal, and that's this repeating charge and the regularity of the building blocks.
Thank you. A question from Francis Westall. If life emerged on land, how did it survive the early high UV concentrations?
Yeah, one thing that you should look at those diagrams from Kevin Zonley and Dave Catling is you'll notice that they're also mentioning haze, because an atmosphere that's reducing and therefore productive to form the nucleobases and the other things that are necessary to put on the bases, that does not have much UV light penetrating to the surface. And I mean, the Simons collaboration has had a long program here, what they call the cyanosulfidic mechanism, which we take exception to because it requires large amounts of hydrogen cyanide in an atmosphere to rain onto a surface where the surface is itself exposed to high energy photons. And we think that those two are quite incompatible. But you're right, after a while, the hydrogen clears after some time. I mean, depending on how big the impact is, 2 million to 20 million years. And then at some point, the atmosphere unshielded by oxygen it is no longer hazy, and the UV light does come to the surface. And now the organisms either must take refuge, right? Which of course there's plenty of places to take refuge for in an aquifer, but also they also eventually get to use that light. But yes, initially what's very important to understand is that all that chemistry on the surface of the Earth is taking place between a productive, reducing atmosphere that is also hazy, that is preventing the penetration of destructive high energy photons.
Great. As a last question in the last couple of minutes from Creon Levitt, you mentioned NASA's conservatism with respect to agnostic life finders, and Creon asks, why is that? Why do you think they are not flying these kinds of missions, and what could be done to perhaps encourage such missions?
Jim Green is probably listening, and he's taking out a contract on my life. It's a fascinating story. I mean, obviously in 1976, Viking, on its own terms, found life. Klaus Biemann's mass spec, which allegedly disproved the existence of organic material on the site where Gil Levin and Norm Horowitz were finding metabolism signatures of life. The mass spec was taken to rule out organics there, but we have actually, I mean, my only real contribution to this area was to point out that those results were misinterpreted. But I did write a piece on my primordialscoop.org blog where I had gotten the opportunity in 1999 to referee for NASA, and I was in the Lunar Planetary Institute and had access to the library where we had the entire mission logs. And what you got the impression of when they found these positive signatures of life by Norm Horowitz and Gil Levin was they were afraid of the results, right? And think about it, it actually makes sense. If I say to you, I've just found life on Mars, think of my life for the next 2 months. I mean, it's a world of hurt. I'm going to get, even before the age of the internet, I'm going to get a lot of time. If I say I haven't found life, everybody's going to say, oh yeah, okay. So we see what I would call we see fear in those records. That is that if you found life, it's sort of, oh God, what are we going to do next? And that's a problem. But if we haven't found life, we can sort of just go back to work. And I talked to a lot of NASA administrators, and they're quite rational about this. I mean, many NASA people look at the Viking results as a failure because it was not definitive. And of course, from my perspective, it was not a failure because it was not definitive. It's an interesting result, and it's an interesting way of looking at how you do exploratory science. You can't be afraid to discover the result that you're looking for.